So now we move to the other session, and it will be chaired by Dr. Sylvester Atombo from the University of Zambia, and the rapporteur will be Dr. Maganga from Kabarak University. So we also have a keynote address in this session from Professor Msseesa Diale from the University of Pretoria. Yesterday, I think we had problems having her greet us, but now she's presenting. I think she'll greet us. So let's have the chair of the session, Dr. Hatombo, introduce Professor Diale. So Professor Dr. Hatombo and Dr. Maganga, please take over. Thank you.
Hello, good afternoon, everyone. Good afternoon, everyone. Hope you are getting me loud and clear.
Good afternoon.
So before we continue with the program, may I just know that the presenters for this session are available. Yes, I can see Professor Diale is already there. Maybe the next presenter is Pamela Kajumba around? Kajumba Pamela?
Yes, I'm around.
Okay, good. The next presenter is David Osionganga. David Osionganga is around? Okay. Okay, we'll see later. The next presenter is Robinson Omoni.
I'm around.
Very good, thank you. The next presenter, Tusime Swala. Tusime Swala.
Hmm?
Wow. Tusime Swala is around? Not around.
Yes, hello?
Okay, good. So we have now only David Sionganga not present. So we now go to the preliminary keynote speaker, but before that, the session is on solar energy storage, energy storage, fuel cells, batteries, and the superconductors, supercapacitors. So may I just introduce to you formally the keynote speaker for this session, who is Professor Msseesa Diale. Professor Diale comes from the Department of Physics, University of Pretoria in South Africa. She is the chair of South African Research in Clean and Green Energy. She is an active member of South African Institute of Physics, also American Vacuum Society, as well as Materials Research Society. Currently, she is working on perovskites and hematite materials in her fully developed lab in Pretoria. She has managed to replace ITO, which is the indium tin oxide, in polymer solar cells, and her work actually is being commercialized. She's also specialized in photoelectronic materials with a specific focus on photonics in UV detectors, solar cells, and photoelectrochemical water splitting. Professor Diale is a fan of thermodynamics, as temperature changes how materials and devices behave. So in a nutshell, those are the key areas of Professor Diale. So with that said, may I welcome Professor Diale for her keynote speech. Professor Diale, please.
Good afternoon, everyone. Can someone share my slides, or do you want me to share them from my side here? Can I share my screen, or someone is sharing it from your side?
Well, maybe you can share it yourself, since if you can able to share it on this forum,
Okay.
Go ahead and share, please.
Okay, so everyone can see my slides. Thank you.
Yes.
Okay, let me just go to the beginning. Yeah. Young people there, you must be able to help us with. I've removed the video because internet may become unstable, but you don't need to see me now. But many people know me. Thank you so much, organizers, Professor Wambura, for inviting me to this very important meeting of Msseesa in East Africa. Unfortunately, because of COVID, I cannot be there. I really wanted to be in Kenya. It's unfortunate COVID is in control of many of the things that we do. I'm going to speak on materials for efficient energy storage and focus my case on hydrogen, on what is that we have achieved from my lab. I generally collaborate with Dr. Samiji, and we have got students that we are co-supervising, and we share also the materials and also the equipment. And then I also collaborate with Dr. Munyati from University of Zambia and Dr. Hadwambo. And we do a lot of nice work like this one that we're talking about for polymer solar cells. So it will be nice for people to know that my name is Mantsai. My last name is Diale. Moche is my middle name. So I'm in the Department of Physics at the University of Pretoria. So I am occupying a South African Research Chair Initiative in Clean and Green Energy. A chair is someone who has been tasked with the work of training students. So in my training of students, I also work with many African countries, which I really love doing. I love going to Tanzania. I love going to Zambia. I love going to, I enjoy going to Egypt. You know, those, like Zambia, it's my second home. I have heard the Zambians when I said to them, I think I'm going to get a house in Tanzania. Say, no, you belong to Zambia. So our group working on polymer solar cells, we have got 3 MSc students working very closely with Dr. Munyati in Zambia and Dr. Adwambo. And then we also work on perovskite solar cells where we have 2 PhD students and 4 MSc students, and we have work on solar water splitting to store hydrogen, where we're using hematite. We say in rust, hematite is rust. In rust, we trust. So we have 3 PhD students and 3 MSc students. So I have got, you can see that I have a mass meeting of students, and I still find people applying to my group, and I'm interested in actually a student who registers at the home institution, and then we share, because I don't want my collaborators to lose students, but you can send your students to my lab to use my equipment and also some other equipment that is available in South Africa. Okay, so climate change. You can see that place, a top view of heavily polluted day in Beijing, China. It was in 2019, 2015, November. That is an example of what is that we need to be doing in Africa in particular to avoid this kind of situation. Though we are busy deforesting and adding more woes to our climate change issues, but we are still safe. We can do better with clean energy. Also, as the world population is growing, the world population is dictating to us that we need to have new energy and not rely on the fossil fuels as Africa, we really have to invest a lot in research, in devices, in the last outputs of giving our continent clean energy, and we are the ones who can do it better. You can see that from 1990 and the prediction up to 2100 is that there's going to be a growth, a big growth of number of people in the world. And it is said that actually Africa will be having a very good number of young, vibrant people who will be looking for opportunities to do better. And then this, the reason why we're doing this kind of studies is because of the globally energy-related carbon dioxide emissions and annual changes since 1900 to this year. You can see in this slide here that this thing is growing. This carbon dioxide in the atmosphere is going up and up and up. Though, according to this article here in Nature, because of all lockdowns, temporary reduction in daily global carbon dioxide emissions were recorded because there were no economic activities. This gives us an idea that we can do better, especially in Africa. Okay, now what is this hydrogen economy? My slide has moved a bit, but it's okay. You can see that with hydrogen, you can power vehicles. It's a synthetic fuel which can reduce carbon dioxide in the atmosphere. It can be extracted from oil and biomass, and it can be used in producing fertilizers from ammonia. Hydrogen is found in ammonia. Hydrogen is found in oil, in biomass, and it can be used in refining metals and many other uses, even heating, like cooking in the houses with gases. And therefore, we need a lot of infrastructure throughout the world so that we can use this hydrogen as our next future electricity. In particular, I'm interested in hydrogen as a replacement for gasoline in transport. So this slide here shows that you can get from renewables in the planet just using your solar panels, using your green stuff, as I was asking Charles about his dye, and with the wind tunnels, windmills. So we can actually clean up the environment. These are our types of renewable energy systems. Transport, as I said to you, I'm very interested in seeing hydrogen being used as a fuel. It has been said, there are articles, particularly from Germany, that during lockdown, it was discovered that hydrogen can be a replacement for fossil fuels. We have seen how the oil price has dropped so drastically. So while the oil price is down, it is our chance now to go in there and revive the economy of Africa through using hydrogen as our gasoline, our fuel for transport. So you can see here the first car, the black one there, it's Elon Musk, nice cars. And the second one here, you can use it in the machinery, and there are growing number of hydrogen stations throughout. This is comparable with battery cars that needs to be charged. Okay, these are global hydrogen stations. How can I put this thing down? All right, global hydrogen stations where you can get gasoline that is called hydrogen. I call it gasoline so that we understand better. If you look here around Europe, there is a cluster there. And then some of them there are around the East Asia and Japan there, and very few in the US. And for us, we have nothing. So it is said that Japan has the largest number of public hydrogen fuel stations, 96, ahead of Germany, which is 60, and USA is 42. So there is also an opportunity to do business in installing hydrogen in our existing fuel stations. All right, now let's go to how do we extract this, how do we use the sun as, and save the sun, store the solar energy in hydrogen fuels. So we use what we call a photoelectrochemical cell, which actually, the first picture there, your photoelectrochemical cell, it has got a photoanode and a counter electrode. So the photoanode here is like a material for a material science here. When the sun shines on the material here, which is a ceramic, which is a semiconductor, electron hole pairs, you can see a hole here, an electron are extracted from there due to the right band gap of light, and then electrons are then attracted to the metal part of that photoanode, and it, with a bias, it is given a chance to travel to the counter electrode, and the hydrogen goes into the water or a solution where it produces oxygen as a gas and the hydrogen as electrodes, ions. So the hydrogen ions will go to the counter electrode, which is actually a platinum counter electrode. Platinum is one of our metals here in Africa, and because of our behavior, we send it overseas and it come back to us very expensive. But if we were making it ourselves here, processing it, it was going to be cheaper. So at the counter electrode, the hydrogen combines with the electrons and it forms the hydrogen gas, so that with light of the right band gap shining in the solution, you can split water into oxygen and hydrogen. All right, next slide then. It's the semiconductors that we need to use as the photoanodes or photocathodes, the anodes or the electrodes, must have some important characteristics, like the semiconductor must have a suitable band gap. It must have suitable band positions, I'll explain later. It must have low overpotentials. We expect also efficient charge transport, and that semiconductor must be stable in solution. This is our energy band diagram. If the light that we are shining there has got correct band gap, like between 300 and 400 nanometers, you'll only access 5% of the electromagnetic radiation. If your band gap lies between 400 and 700 nanometers, you'll extract 43% of the visible light. And then if it is beyond 700, you will only get, it will be too much of the 52% of infrared radiation. Okay, these are the band positions. Here, this is the most important slide for the work where we say it is materials development for as we said, materials for efficient energy storage. These are generally most of the ceramics and materials that have been used. You know, we know silicon is there with the right band gap, and then that will be able to absorb in the visible. And then we have got cadmium selenide, 1.7 is still a good band gap. It will absorb in the visible, and it has been used by other people. And then we have got silicon carbide. The band gap is too big, it's UV, so we are going to get only 5% of the electromagnetic radiation if you use the ultraviolet section of the electromagnetic radiation. And, you know, I look at the many materials here which have got a bigger band gap, and I'm asking myself, what is that you can do to replace them? In this picture here, let's first look at the band gaps. The gallium arsenide is 1.4, cadmium sulfide is 2.4, zinc oxide is 3.2, copper oxide 1.5, hematite, this is our iron oxide, where we say in rust we trust, is 2 electron volts, and then titanium dioxide is 3.2, tungsten oxide is 2.8, copper oxide is 2, and bismuth dope, vanadium oxide doped with bismuth is 2.4. So when you look at this picture, the green is your conduction band, and then the black is your valence band. You know that in a semiconductor, for a semiconductor to absorb, we need the conduction band and we need the valence band. The hydrogen evolution occurs at the valence band, and then the oxygen evolution occurs at the conduction band. Let's go back. So we have here hydrogen plus hydrogen. This is your top band, which is hydrogen evolution reaction occurring at this position, and then oxygen evolution occurring at this position. So when we look at all these materials and what we are doing in Msseesa with different materials, you ask yourself, which material will be suitable for us to produce hydrogen from semiconductor electrolyte device? If you look at all of this, the first people who did this work, Honda and his colleague, they used titanium dioxide. And since then, many people are using titanium dioxide in many different devices, including dye-sensitized solar cells. So I continue to ask myself, can we replace titanium dioxide also in dye-sensitized solar cells so that we can harvest a lot of the solar energy? Because with 3.2 electron volts, we're only going to harvest very little, which is 5% of the electromagnetic radiation in the wide band gap, and even zinc oxide and also silicon carbide. But then we have found that hematite is the better electrode for us. You can see 2.8 or anything that lies around there, according to this, between 400 and 700, you'll harness more than 40% of the solar radiation, which is very important to this kind of studies. So efficient charge transport is that as the light shines into the semiconductor with the correct band gap, and then charge separation, electron hole pairs are created, then these electron hole pairs that are created, they had to travel through this material, the electrons to the conduction band and the holes remaining in the valence band. If the distance here, the diffusion length is too big, then recombination will occur, and we want to avoid recombination so that we are able to get reduction to produce hydrogen and oxidation to produce oxidation. Some of the properties that are necessary that we talked about, if we look at some of those previous slides, I will quickly go back to the previous slides. The requirements, we have spoken about the suitable band gap, and I've just explained that, and the band position, the low overpotentials, the total potential required to drive the photoelectrochemical water splitting is defined by this equation here, where 1.23 electron volts is a thermodynamic potential value for water splitting, and then eta anode and eta cathode represent the overpotentials at the anode and the cathode respectively. And N other is the voltage drop from other resistances in the electrochemical cell, such as solution resistance, contact resistance, and many other resistances. And we must be aware that we are still working with a normal diode. It's just that this time our diode is in the water instead of being a metal and a diode or two semiconductors together. Some other researchers have used two semiconductors together, but the results are still not what we were interested in. Another important requirement for a semiconductor to be used in the photoelectrochemical cell is that it must be stable in a solution. Such chemical industries like cadmium sulfide, zinc oxide, molybdenum disulfide can easily undergo corrosion in photoelectrochemical environment depending on their pH. And on the contrary, titanium dioxide, the vanadium oxide doped with bismuth and hematite, this iron oxide, we call it hematite, have shown great thermodynamic stability in a PEC device due to their slow decomposition reaction. Let me go back a bit and say something here, that if you look at hematite, it's 2 electron volts, and then the other ones that are considered efficient and better, the bismuth dioxide is vanadium oxide doped with bismuth is 2.4 electron volts. You'll forgive me, I'm not a chemist, guys.
Prof. Msseesa?
Hello?
Prof. Msseesa?
Yes, sir.
Yes, please, you have 10 minutes remaining, 10 minutes remaining.
Okay, thank you very much.
Yeah.
Thank you very much.
Okay.
I will be able to cover the time. I just wanted people to see the material side of this. And then titanium dioxide, you can see that even though it is stable in water, it has got a very big band gap. That's why hematite becomes attractive. All right, let's continue. So the advantages of hematite, this red soil, which is seen in many areas here in Africa, is your iron oxide. It has a small band gap. It is very abundant. It's chemically stable in water and solutions. It has a suitable band gap position for oxygen evolution reaction. But some disadvantages about this is that you have never seen rust being a conductor of electricity. So it has got a pure conductivity. It has got a short lifetime of excited state carriers. It has got poor oxygen evolution reaction, and it has got short diffusion length. So what we need to do in research is to correct these disadvantages. So then we chose to focus on hematite, and there are different ways of making this hematite. Synthesizing it is solution-based, hydrothermal, spray pyrolysis, chemical vapor deposition, and electrode deposition. There are still many more. So the strategies to improve the hematite conductivity has been nanostructuring. Many people have spoken about nanostructuring, doping of the material, forming the heterojaction structures, using the very material that has been spoken about in slide number 11. For example, we have made a heterojunction structure of copper oxide and hematite, and we have seen the photocurrent improved. And we can use a cold catalyst and the plasmonic enhancement of using metal nanoparticles. These are the different achievements by many other people of making structures, nanostructures of hematite. You can see nanorods, dendrites, nanotubes, nanosheets, nanocones, cauliflowers, and generally it has to be mesoporous. So nanostructuring, in the results that we have found, is that it has given photocurrent that is better. So if we compare hematite morphology with preparation methods and the photocurrent. We find that you can have a look at the whole thing. I have shared this presentation with everybody. It is there, you can get it. Is that you can see that the photocurrent can increase. Look at the nanorods, 1.3 milliamps, and also nanotubes, 1.3 milliamps. So we can use the nanowires and nanotubes to make our hematite. So these are heterostructures where in our lab we have used copper oxide and iron oxide onto fluorine-doped material, fluorine-doped substrate, and we have found that the energy transfer has been very good using the solar energy. We have got this equipment, we have built this equipment in our lab. Other co-catalyst materials that has been used is noble metal oxide like iridium oxide, amorphous phosphates like copper, this is supposed to be platinum, borate, which is nickel, bismuth, and oxyhydroxide. Okay, the plasmodic effects, the metal inside any material helps with the scattering of light and improving the absorption and emission throughout the structure. So some of the results that we have found in our lab is that we have published a paper now where we have used the film thickness to see if we can find better photocurrent on this kind of work. And then let me just quickly run. The photocurrent improved as we shone the light on this material. So current density of iron oxide prepared using a method called deep coating, comparing it with spin coating, comparing it with both deep coating and spin coating. And we're able to find that there is an improvement, and we chose this deep coating. Why deep coating? Is because when you dip the substrate into the solution, it makes a rough surface, a rough morphology, which is very good for the solution to penetrate the hematite in such a way that your photocurrent is improved. We have done impedance measurements. How am I doing on time, Dr. Twambo?
You have 3 minutes.
Okay. Then we have published this paper. You will be able to get it from our website. If you don't find it, you just send us an email. We can send it.
Can I interrupt, please?
Yes, sir.
Can I interrupt, please? The chair of the session, this is a keynote speaker. She has 30 minutes to present.
Yes,
and,
yes, I was timing 30 minutes, yes.
So let her present till 3:45 p.m. and then we have 15 minutes discussion.
We started at 3:05. Anyway, it's okay. 3:05.
Can I enjoy?
Okay.
Can I enjoy that?
Yes, please go ahead.
Okay. So that's a paper that we published in Surface and Interfaces. Yes, thank you so much, Dr. Mwambura, for helping me to improve that. So another work that we have done was to look at what is the effect of annealing on the photocurrent. So this is how the experiment was done. And then we were able to find this rough surface. You can see that it is not a smooth material, the hematite. And then when we look at let me get something that can help me to see very clearly. On the nanostructuring, when we look at, on this particular area, the results thereof is that we find that the method of preparation is very influential in giving the size of the nanostructures on the surface here. You can see your A, B, C, D, E, F, G, H, I, where you can see where the nanostructures are becoming smaller. And generally, when the smaller the nanostructures, the better the photocurrent that we have found. Some of the results here on the structural properties is when we're looking at the annealing temperatures, because the temperature will be able to tell you how far you will go before you crack your film. You can see here the absorption coefficient improving you can see that if you go from 500, which is a black curve here, and then you go to 600 and 700, there's not much difference. But if you go to 750, you are able to improve your absorption very well. So we have got the results that will tell you which part will we use. After we have done this, we find that we're able to work on our band gap for this hematite. You can see that with the annealing at 500, it gives you exactly 2. But if you anneal at 750, you can lower the band gap. All right, now looking at the photocurrent, we have already now understood that the 500, we can now compare only the 500 and the 700. You can see that your photocurrent increases when you anneal at a higher temperature of 750 degrees Celsius, while many of the papers that we have used before, they only all anneal at 500 degrees Celsius, which means that they are losing some photocurrent by not going higher. And then in the previous slide, we have seen that if you anneal at 800 degrees Celsius, the absorption also drops. So the photocurrent at 750 degrees Celsius is 300 millivolts, which is a great improvement for this kind of work that we are doing. So we have compared the flat band potential and we took the samples, the flat band potential and the carrier density. And we found that the 750 was giving us better results, which will be very valuable for us. So what is that we are looking for? We want a very good photocurrent, which a cathodic shift of 300 millivolts of the onset potential was achieved due to annealing at 750 degrees Celsius. All right, the PE, the photoelectrochemical performance of this hematite, you can see the resistivity there in kilovolts, where we are able to work better with the 750, but we still compare the 750 with annealing at 500 degrees Celsius for this work. All right, and then we have published this paper. So all these results that I'm giving you are published by my PhD student, Panan Kiesman, and then my collaborator from the Department of Chemistry, Dr. Nombona, where we were looking at the multi-layers of hematite on fluorine-doped tin oxide. Recently, with zinc oxide nanorods, we have discovered that actually fluorine-doped tin oxide gives us better electrical characteristics under dark current, better than ITO. And the reason why we are moving away from ITO is because indium is an expensive material, and it is believed that it is being depleted from the Earth atmosphere. So this FTO, it's a future material. All right, we found that we had another result of the heterojunction. And then our heterojunction, you can see that here we have made the nanostructures that are very nice, around 100 nanometers measurements here. And the average size of the nanostructures here is 35.3 nanometers with the diameter of about 6.1. So as we work with this, we have been able to clearly say that if we take hematite and make a heterojunction with copper oxide, we are still doing a study of the thickness of the copper oxide onto hematite to improve the photocurrent. But thus far, the XRD results shows you that in that heterostructure, you have got pure hematite here, and you have got pure copper oxide here, and we have the heterostructure of copper and hematite in this red curve. And then the Raman spectroscopy measurements are just confirming what XRD has said to us. We always want to do both Raman spectroscopy and XRD. So then if you look at the hematite alone and the heterostructure, you find that the absorbance is not really changing that much, but you can see that the heterostructure is improved a bit. And then the band gap of the heterostructure is a bit less than the band gap of hematite alone. And then let me skip this slide and go to the photocurrent measurements. You can see that the photocurrent measurements here, you can't see the dark current of iron oxide because it's so low, it just became a flat line. But of the heterostructure, you can see it's a very nice curve of for the solar energy issues. And then can you look at D with the copper oxide alone, you can see the difference between the small values that you find in copper oxide alone under dark and under light, and then look at the heterojunction. In the heterojunction, both the under dark and under light are very close to each other, which shows that we have to do a better work on both. All right, then we did impedance spectroscopy measurements where we're looking at the sample, the iron oxide and the iron oxide with copper oxide. And then we found that heterostructure gives better results than pure iron oxide. So we have published a bit of number of papers from this work since we started this some years ago. You can see that we have got up to 10 publications in our group, and in bulletins, in journals that are credible. And then in summary, I would say to improve the photocurrent in photoelectrochemical measurements, one needs to use some strategies like nanostructuring, formation of heterojunction, and doping, which we have not included here. Also, the method of deep coating gives a better or highest photocurrent as compared to other measurements. And the photocurrent always improved from 5.3 to 1.3 volts versus the reversible hydrogen evolution. It also resulted in the shift of 300 millivolts of the onset potential. And this use of nanostructured heterojunction of hematite on porous copper oxide gave 19-fold increase in the photocurrent. So all that we are looking for is to increase the photocurrent and using different methods for improving the electrochemical device. Thank you very much for listening to me. I want to acknowledge my funders, the University of Pretoria, the National Research Foundation, and a private people called Motsepe Foundation. Thank you.
Thank you, Professor Diare, for that wonderful and lengthy presentation. So on behalf of everybody, could we really thank Professor Diare for that report? Now, we shall go straight to some discussions as well as some clarifications for 15 minutes starting now. Are there people with burning questions or clarifications for about 15 minutes? The floor is open, please.
Yes, my name is Eva Shana from University of Dar es Salaam. I have a question to Prof. Manzai, and my question goes on your slide number 31. Your slide number 31.
Yes, I'm going there.
Yes, there. So my question says, why when you are near at a temperature more than 750, that is to 800 degrees of Celsius, it reduces the absorption coefficient? What is the reason behind it?
The reason behind this is that the material becomes hardened and it starts cracking. The reason why the photocurrent goes down is because the material after 750, the annealing thereof makes the material hard and it cracks. Therefore, if you think about a cracked material, it is no more compact. Therefore, you cannot measure, the charges are not moving as they ought to. Are you happy?
Okay, any more? Yeah, any more clarifications?
Yes, I have.
Sana, okay.
I have on slide number 13.
I think the previous person did not understand.
No, she got it, I think.
Okay, Sana?
Thank you. To slide number 13.
So please let me have the name of the person, the question, and also the where you're coming from, so that we have order.
Rusato Majura from University of Dar es Salaam.
Okay, good. Question?
Yeah, my question lies on this part that the thermodynamics suffers a lot on resistance from other resistance, such as solution resistance, contact resistance, and a resistance in the external wires. Is there any approach or solution you have used to improve so that the voltage increases?
What we have done is that we have discovered that if you put the nanostructuring with if you look at the method of preparing your material, then already the method will help you to reduce the external resistances. You know that in a normal diode, we have a very important factor called series resistance, and it is there at all times. And how do we reduce the series resistance, the normal series resistance in any diode? It's when we are cleaning the material properly, simple mechanical interactions. The way you interact with the material, it has to be a pure material, number one. When it's a pure material, your resistance will be lower. And also, as you continue handling your substrate, the substrate here, I'm speaking of the hematite or your semiconductor or your ceramic material, you must make sure that you continue to be very careful that you are working in a very clean environment so that you don't have any contaminations from outside that will increase the resistance of the electrochemical cell such that your voltage will be lower. So the cleanliness of the environment is very important.
Oh, thank you, Prof.
I have a question.
Yes, please.
My name is Professor Samir from the School of Electrical Technical University of Kenya. I would like to first thank Professor Mansi for a very good presentation. I'm also learning in the material science. I'm an aerospace engineer, but in a different area. But I wanted to ask her a question regarding the annealing process, that why when you anneal at 800 degrees C, the band gap decreases. Can that be clarified once again, please?
I blame that. Let me go to the band gap slide.
Yes, please.
Okay, am I here? Here.
Yeah.
800.
Yes.
Oh, okay. No, we were not looking. The 800 is not. Number one, Prof, I really like it when an engineer joins the material scientists.
Yes.
That's how the Americans are winning. I have worked with the Americans very closely because I'm a member of the MRS in the US. I've worked with people from Israel. I have worked with many different groups, people from China. And when an engineer is involved with the scientists, the device that we are going to come up with is usually a very good device. So the reason why you see as if there the band gap of 850 is lower there is because we're looking at 750 here. We're not really focusing on 850. It's like 850 and 750 are giving you the same band gaps. But think about the movement of charges. What do we call that? In physics, we speak of tunneling. And then when the material, I said to the previous caller, the lady who asked the first question, that if we anneal the hematite at 800 degrees Celsius, our crystal nanostructure starts cracking. And simple mechanical issue of the fact that it has cracked, then it has produced a defect. And that defect will definitely produce a trap for charges. So charges will be trapped when they arrive there at that crack. Therefore, when charges are trapped, then we expect the series resistance to go high. So since you were looking at the band gap in this particular area, the band gap that we are seeing, that means here the 850 and the 750, when it comes to absorption, there is no difference. But electrically, the 850 is a no-go area. Thank you very much.
Thank you very much.
Yes, please. Any more questions? Clarifications? We still have 80 minutes.
Whilst we're waiting for questions, I want to say to all of us in these organizations that generally hydrogen production through photoelectrochemical water splitting is not very common with us here in Africa. And I would encourage that many of us can work together in this area.
Chair, you can also check, there are some questions in the chat also.
Oh, okay.
Okay. I think you are right. You are right, Mr. Rapporteur. Professor Diale, there's something here that says, hello, Professor Diale, in your introduction, you mentioned that you have students who work on perovskites. My question is, are they doing it through simulation or experimentally? If experimentally, which equipment do you have at your lab for the experiment.
Okay, can I stop sharing? Can I
Yeah.
stop sharing here? Because Sylvester, these young people says we are not good with technology. So let me just end the show so that I can be able to see my people in Zoom and see the chat. I don't see it.
Oh,
all right, no problem.
Just below.
Where?
I think.
Oh, I've seen it. Thank you.
You've seen
You're
it?
right.
Okay.
Yes. We are working on perovskites, and we're making perovskites, and we have done a very nice job with perovskites. There is a relationship that I have started with Dr. Celine from Kenya. It's just that the COVID came in, so we could not travel between each other. So what we are doing in our lab with the perovskites is that we are making the perovskites in the lab. We are using resistive evaporator to deposit the perovskite. We have made the methyl ammonium lead iodide. We have made methyl ammonium lead bromide. We have made methyl ammonium lead iodide bromide, where you have the two halogens there as the parts of the perovskite. We have also started with cesium lead iodide and cesium lead bromide. And we have achieved the multi-cation and the multi-anion into this. So our perovskite is a very, very big job. Some of the publications that we have done is that we have produced the some 2 papers on defects in perovskite. So we do have a very good level.
Sorry, presenter.
Yes, sir.
Sorry, presenter. There's a very interesting question here. The other one is that Rita is asking whether the hydrogen fuel is a very interesting area. Do you mind sharing your research papers or documents on it?
Okay. Yes. Yeah, we don't mind.
Okay.
Who is looking for the publications?
Rita Mwende.
Oh.
Rita Mwende.
Rita, is it Mbilo? Or they're different?
The other one is oh yeah, no, this is okay, it's good. Okay. I think we were done almost.
They are different.
Right.
They are different.
Okay, we are done.
They're different. Okay, no.
They're different,
okay.
yeah.
Let me answer this question.
Yes, please go ahead.
It will be very interesting for us in Africa here with Msseesa to go into the hydrogen research. I work with the people in Switzerland on collaboration on this hydrogen work. And in Switzerland, there is a house at EMPA, it's a laboratory there, where they are already testing the use of hydrogen and solar panels as an entity that is free from the grid. So according to me, it is a good area for us to go into. And I don't know if Rita is a researcher already in the department or is still a PhD student. I'll be very happy to work with you, ma'am. Thank you.
Okay, any last, okay, one last question, please. Any question, last one or clarification before we close this session? Okay, so I can see that we are done. Please let's thank again Professor Diale for the wonderful report. Okay, so now they will go to the next session. The first presenter will be Pamela Gajumba, and please, Pamela, can you go ahead and share your screen?
Okay.
Not showing that.
Pamela?
I'm sharing.
Looks like we have lost the presentation. Hello, Pamela?
Pamela is sharing the folder. Can we help her screen? Pamela?
Yes, if you can.
Okay, fine. So just stop sharing. Stop sharing your folder. Okay.
Did you listen?
Is someone helping her?
Yes, we'll project from here.
Okay, okay.
Okay, no problem, but it went very well. It's so nice. And then I didn't go deep into electrical stuff of explaining what they want. I was just going through the results, just, So we will discuss more next week on how to improve this presentation, all your results.
So Pamela, is that your presentation? Pamela?
Yes.
Okay, go ahead.
Okay.
Okay, thank you, Prof.
You have 15 minutes from now.
Yes, Doctor.
Please go ahead.
Okay, I'm Pamela Kajumba from Makerere University, a PhD student. And I'll be presenting something, one of the objectives of my PhD work, and that is assessment of energy needs for cooking local food as a strategy for designing efficient cooking units with thermal energy storage systems. My supervisors are Dr. Okello, Dr. Karidewa, and Professor Olejagon from NTNU. So that is my order of presentation. Next slide, please. Yes, in the introduction, we all know that energy for cooking is mostly from fuel wood in developing countries, and Uganda is not an exception, as almost 80% of the energy is provided by fuel wood. And currently, to add on to that burden, Uganda hosts a very big number of refugees who all depend on wood fuel. And of course, all this has reduced the forest coverage to that consumption per annum, and it is increasing. Next slide, please. Yes, but cooking is something that has to be done every day, and it requires substantial amounts of energy. In India, there's that research done on energy for cooking, averagely around 1.9 megajoules per person per day. But with all this, a few studies have been done to document energy for cooking. And that's why we are doing this research to understand how much actual energy goes into cooking a given quantity as a strategy to improve design of solar cooking units and other new technologies, and also to inform policy. Yes, next slide. Yeah, so the objective of this was, the specific objectives are to determine energy input into cooking. And this will be also help us to understand the specific fuel. We are talking of other fuels like LPG, firewood, charcoal. And then another specific objective is to understand what is the size of the thermal energy storage that you need for a particular cooking or to cook, yes. So my materials and methods, we cooked commonly cooked foods and consumed foods here in Uganda or even in East Africa. These include maize flour, dry beans, cassava, plantains, which we call matoke, sweet potatoes, and rice. These are cooked under controlled cooking conditions in the lab for us to obtain the energy input for cooking per kilogram. On the right is the image of the experimental setup. We have number one is the energy meter. We have the cooker. This is a electric cooker, 1 kilowatt. And this is plugged into the energy meter, as you can see. So the energy meter gives us the energy output in kilowatt hour. We have the insulated pan, that is number 3 with the lid, where the food is contained. And then we have thermocouples. We want to measure the ambient, we measure the cooking temperature. These are with the data logger, people data logger, which we interface with the computer to record the data. Next slide, please. Yes, thank you. So on top of the controlled cooking tests, we also did some surveys as part of our data collection. This included institutional surveys because we want to get information about what is the commonly consumed food in schools, how much do they cook, how much fuel wood, and what type actually are they using. Because this design will not only be household, but will also be institutional. So we also did market surveys to get the price of this fuel. On the right are some of the analysis equations that we used. Q input, this is the total energy we are actually measuring from the energy meter, but this can also be used to measure the theoretical or to calculate the theoretical energy. Then the specific fuel consumption, that's equation 2. A volume of oil for energy exchange, this now applies to the cooking unit that is integrated with the thermal energy storage or the TESS. Yes, thank you. Yes, and we also had to do, because these are experimental results, so we had to random error, which is like uncertainty analysis. We did error analysis and uncertainty analysis. So the random error is to do with consistency in measurement. You carry out a number of measurements, and then you get the random error to see if I'm cooking maize flour so many times, how consistent is my experiment. On the other hand, the systematic error is to do with what is the measured energy when you compare it to the theoretical energy. So things like what am I losing in terms of to the ambient? Yes, so those are the, yes, thank you. So when we go to results and discussion, this is just a summary of, table 1 shows a summary of what we cooked and the quantity of water used, because of course quantity of water will affect the energy input into cooking. Yes, the number of times.
Yes. Were you in the meeting?
And then the average cooking times. Yes, so mostly we were cooking 500 grams, but we're getting the energy per kilogram, the energy input for consistency purposes. And then the quantity of water used was mostly basing on what is given in most recipes in day-to-day cooking. Yes, next slide, please. Yeah, this is some of the results we got. On the left is the measured energy input. They are a bit small, but we have beans 1, this is the horizontal axis, beans 2, beans 3. Beans 1 refers to dry beans, beans 2 is fresh beans, beans 3 is dry beans that has been soaked for 10 hours prior to cooking. Then we have matoke, that is the next, rice, cassava, sweet potato, maize flour. So in summary, this is showing us the blue part is energy for boiling. This is up to the boiling point, and then we turn down and simmer. So we are looking at this, most of the food items, once you have reached boiling point, you do not require so much energy up to the when it's totally cooked. And this shows us that we can actually boil and turn down the heat, and then the food will get cooked. But when you look at dry beans, that is number one, it shows that you need actually more energy after the boiling. So it would not be advisable to turn down after initial boiling. But the energies are in range. For all the experiments we did, we got averagely, with dry beans having the highest, and then the soaked dry beans. And it's interesting because we can see that when you soak the beans prior to cooking, you actually have some significant energy savings there. So on the right is now a comparison between the measured and the theoretical. The blue one being the measured, and then the dark brown one, I hope that's clear. Oh, yes, the theoretical. But what this shows is that actually the measured energy is much more than what is predicted in theory. And this is obvious because of things like losses to ambient and then evaporation and all that. So, but yeah, it's comparable. So when we go to our institutional survey, what we got from the schools, it was interesting because, of course, schools have different numbers of students, but what we found out is that the food cooked is similar. Most schools consume maize flour and dry beans. And these are the details of what was from each risk. We went to visit different schools. This is a summary for 10 schools. And the quantity of fuel also depends on, of course, what is cooked. But in terms of energy, we had to take this back to our energy. How much does each student consume or require per day? And this is about 0.322 kilowatt hour per student per day. So if you have a number of 1,000 students, you can easily get the total energy requirement per school per day. Next slide, please. Yes, when we go to specific fuel consumption, this is in households, we based our computation on what has been done earlier because we did not do a household survey, but basing on what has been earlier on what a person consumes per day, we had, and then having our results for what do we need to cook this much in terms of energy, we can easily compute the household energy consumption per person and then per household. And that was about 1.8 kilowatt hour per day. This is per household. If you get per day, it is around 0.36, which is interesting because it is similar to what we got from the schools. The schools, we did the survey, we visited the schools, but the household we did basing on what had been done earlier, and the results are in close agreement. For the schools, we had a student consuming 0.32 kilowatt hour per day, and for a household, if you get this, it's about 0.36, slightly more than what is consumed in schools. And now taking us to what amount of fuel we use the commonly consumed fuel and technologies so that we can get the specific fuel consumption in households. And at the end of the day, how much can be saved if you use a more energy efficient technology or fuel. And table 3 shows the summary of what we computed. We used equation 2. Equation 2 was earlier on in the slides. In the analysis, it talks about the mass of fuel. Once you know the efficiency of this technology and the calorific value of the fuel and what energy you inputting, then you can actually get the mass of the fuel. And that's what we use to compute our mass of fuel. This is per household. So we are using our energy input per household per day, and then getting the annual energy requirements for the different fuel requirements. We have firewood when you're using the 3-stone fire, firewood when you're using the improved kiln stove, And these are comparable, but we are seeing that there's at least a kilogram of fuel saving with the kiln stove as compared to the 3-stone. Yes, and all this goes on with, the more you improve the technology, for example, if you have a fired clay stove, you'll cut down on how much fuel you are using as compared to the old metal stove. And this will, of course, reflect on this energy savings, the cost of fuel, and the emissions, which we have not put here. Next slide, please. Yes, when we were talking of now why we did this research, in that we wanted to improve or to size suitable storage for cooking units. So in our earlier work, we designed a cooking unit, which is together with a storage system that is shown in the schematic of figure 4. Actually, briefly to run through this, the schematic, you have the red part is the heated or the hot test with sunflower oil. So this sunflower oil, once you open a valve, it flows to the cooking unit. This is gravity. We don't have a pump. We control it by the manual valve. So the quantity of oil for energy exchange is what we're interested in. Because when we did this work, this is an earlier work that has been published. When we did this work, we tested the cooking unit to cook rice and dry beans. And the rice got cooked, but the beans were not cooked. So with that in mind, we're like, if we had known how much volume of oil that we needed to cook the beans, then the storage could have been sized accordingly. So that is why this other work came in. So once you know how much oil and a volume do I need as a heat transfer fluid to exchange heat.
Pamela, can you please wind up? Is time up?
Yes,
Can
okay, thank you.
So
next slide, please. So this is a summary of how much energy input we needed, and now we took it to the volume of oil for our storage, is what is summarized here. So if you have, this is at input and output, what comes into the storage, the temperatures at 180 in coming in and then leaving at the storage at that. Okay, next slide, please. So in conclusion, we subjected local foods to controlled cooking tests in the lab. Dry beans required the highest, that is about 1.65 kilowatt hour per kilogram. And we found that soaking the beans can save about 0.5 kilowatt hour per kilogram. Our random error and systematic error were moderate, so the experiments were consistent. Then institutional survey revealed that about 2.6 kilogram of firewood is used to cook dry beans, a kilogram of dry beans. Yeah, those are my sponsors, ISP and ENP.
Okay, thank you very much.
Thank you. Yeah.
Thank you very much, Pamela. We'll have comments and questions at the end of the session. So can we straight away go to the next presenter, who is Robinson Omon? Robinson? He was there at the start. Robinson, please.
Hello.
Yes,
hello.
Please.
Are you getting me?
Can you share your screen?
Okay. Yes, I hope everyone is seeing my presentation.
Go ahead, please. Go ahead.
Well, thank you, Doctor. Well, my name is Omoen Robinson, and I am a a master's student from Makerere University. I'm being supervised by Dr. Ukeno Dennis and Dr. Karade Wanyenga, both of Makerere University Department of Physics. We carried out a study on performance analysis of thermal energy storage system integrated with a cooking unit. Fast forward to the background of this study, we know that nearly 75% of households in developing countries still relies on wood fuels for cooking, in which cooking is carried out by burning fuels in a locally designed stove, and this stove are very efficient in energy conversion. So there is actually a need to identify and develop a clean source of energy, such as electricity and solar for consumption by the majority rural population. And among these alternatives, solar energy can be considered one of the most viable options. The different type of solar cookers, as we know, that are on market are the box type and concentrator type. So the solar type, those box types and the concentrator type do experience the intermittent nature of solar radiation, and this need to be which makes it a disadvantage for use. So there is actually a need to develop an indirect solar cookers that uses thermal energy storage system to store the energy for later for application when the sun radiations are off. Several storage systems with and without cooking system unit integrated have been studied. Now in them, there have been problem of heat extraction from the storage. So a simple design of heat storage incorporating a cooking unit will solve the problem of heat extraction and improve the cooking performance of the test cookers. Now, the objective we have solved in this study was developing and determining the thermal performance of a test system integrated with a cooking unit with the water and thermia B as test materials. Now, in design, the test system consisted of two units, that is the storage unit and the charging unit. Down there, this small one is a charging unit. Inside it is an electric heater and a thermocouple that monitors temperature of the liquid being heated. The liquid we're using in turn, water, then the thermia B. Then this is a storage. The main part of interest in this diagram is the cooking chamber, which is embedded on the top cover of the inner cylinder. So this is made of an aluminum pan, such that a person cooking should also be able to use another aluminum pan that fits exactly circumferentially and basally, so that heat extraction is from the storage into the food. And this eliminates factors like using long pipes that would allow losses of heat, and the use of pumps is also prevented, and this cut on the cost. Then this has been our experimental setup. So to monitor temperature inside the storage, 5 thermocouples were mounted at different points, but of course at same distance from each other along the vertical distance inside the pipe. Now, this thermocouple from the storage and the one from the boiler were connected to a data logger that is interfaced with a computer, and the computer records the data direct. The data logger was configured to measure, to record the average of 100 readings after every 1 minute. Now this was our completed, the fabricated test system. As you can see, correspondingly with the experimental setup I explained up there, this is our computer. This is a data logger, and these are the cables from the storage, and there's one here from the boiler connected to the data logger. So basically that is the future. Then the parameters that we are interested in were the charging time, that is how long it takes to charge the storage, heat retention capacity, the thermal stratification inside the storage defined by equation 1. Then the charging energy defined by equation 2. Charging exergy, and clearly charging exergy, you see it is the difference between the max, okay, the total energy achieved during charging minus the energy the system would have if it were to return back to the equilibrium state. Then the efficiency of interstruction, this was determined by first of all heating the storage up to a maximum point, then evaluating the average temperature inside the storage. Afterwards, after which a measured quantity of water is added into the cooking chamber and heated and allowed to heat up to a maximum point also. Then at that point, the storage is again, okay, the average temperature of the storage is again established, and we evaluate the efficiency using that expression. So basically, these are the results from my charging, okay, from our charging of the test system. Graph A represents that of a water state system. Now, when you look at that graph and looking at the key, T5 correspond to temperature at the surface. Of course, this device is charged based on thermosiphonic principle, in which the hot liquid from the boiler rises, of course, because of this difference, rises in the upper pipe and end up in the storage, and this cycles continue until the storage is fully charged. So T5 correspondingly is up here, as you can see, and T1 is the base temperature in the storage. So, which means the top temperature in the storage, the top level of liquid in the storage takes up first, followed by T4, T3, until the base also attains a certain high temperature as thermosiphoning continues. Then similarly in graph B, this is an oil test system. The same pattern is observed. However, oil having high storage density, we can charge it up to a temperature of around 200. Meanwhile, water, we were able to only charge to around 89 because bubbles started developing in the storage, and this stopped increase in temperature. So, but for oil, we were able to reach a temperature of 215, and we stopped there. Then during the heat retention process, the storage was charged. Both the water test and the oil test were charged to maximum temperature. Then they were allowed to stay over a 14 period while monitoring the temperature inside. So at this point, it corresponds to the maximum temperature attained after charging. Then it was allowed to stay for a 14 time period. Then after the 14 time, okay, period of heat retention, the temperature were measured, and for water, we were able to find the storage at a temperature of 68, and that of oil was charged to 200 initially. After heat retention period for 14 hours, we were able to get an average temperature of 108, and this temperature is high enough for cooking, say the following day before charging could start. Then stratification was a measure was used as a measure to define how efficient is this system in the energy storage. So a high stratification number is an indication of a high charging energy and of course charging exergy. So the water test system achieved a high stratification number of about 86. But when you compare to that of oil attained a stratification number of 82, and correspondingly charging energy were also achieved. Maximum charging energy were achieved at these high points of stratification number. Now, in one other experiment, cooking was carried out while charging the test system, and this is the temperature profile inside the storage. But of course, this was carried out with the oil only. But a similar test was also carried out with water, and I must admit that this system were so good ability to be used for cooking during charging. So in this case, the test was charged, the oil test was charged to about 160. Then a half kilogram of bean was added into the cooking chamber and cooked. Of course, as you can see, the beans and water at about temperature of 24 was added into the chamber, and the temperature in the cooking chamber kept on rising up to a maximum point of about 98, and at the level of there, and that is fairly a good cooking temperature. And the beans was able to get ready in about 2 hours 10 minutes there. Now this is a summary of thermal performance parameters of the test system investigated.
You have 3 minutes remaining. Robinson, 3 minutes remaining. 3 minutes remaining.
Yes, yeah. I'm summarizing. So the charging time for water was 2.3. Meanwhile, that of the oil test was 7.8, because it was supposed to reach a fairly high temperature that would allow for cooking. Then temperature after irritation for 14 hours, as I said earlier on, was 68.8 averagely, then 108 for oil. Stratification number for water was 94. Meanwhile, that of the oil test was 82. And charging energy in megajoules in 1 hour. As I said, the stratification number determines the amount of energy stored and that of the SRG. Then lastly is the efficiency. Water showed a very low efficiency compared to the oil test, probably because of water having low energy storage density. Then in conclusion, we arrived and said, though water has low energy storage density compared to oil, the water test system achieved a high charging energy than oil. And oil test system, however, is a more efficient storage system in terms of heat retention and cooking performance. And we also concluded that heat extraction is highly improved by embedding the cooking chamber within the storage system and using test materials of high energy storage density. Now, these are some of the outcomes of the cooking experiment carried out. A is raw beans added into the cooking chamber. B shows bean boiling. And of course, C is ready served bean. This was an experiment carried out in the morning after heat retention using the oil test. So after the 14 hours, the temperature inside the storage was still high enough for cooking something that you can prepare like for breakfast. So this was macaroni added into the into the cooking chamber and put in the storage, and this is the outcome. This is rice cooked with the water test system during charging. We appreciate MP Capacity 5 project, ISP through UG1, Msseesa, and ADBH. Thank you.
Okay, thank you, Robinson, for keeping up to time. Now we go to the last presenter, who is Tusime Swale, please. Can you share your screen? Perhaps she's around.
Chair, we also have Osio.
Has he come now? This one wasn't there. David is back now. Okay, first let's go to Sime.
Okay.
Yeah.
Are you hearing me? Hello?
Yes. Yeah.
Yes, please go ahead.
Okay. Is it shared? Am I lost? Are you seeing my presentation?
No, we're not seeing it. Can someone help you nearby? Okay.
Maybe someone could
It's coming
post it
up
for
now,
me.
yes. Yeah, but good. So you can start now, please.
I can start? Okay. So Tusime Swale, a PhD student from Makerere University. My supervisors are Kaidewa Nyenga, Dr. Kaidewa Nyenga, Dr. Dennis Wakelo, and Professor Ole from NTNU University of Norway. I'm going to present about one of my PhD objectives, that is an experimental investigation of the performance of a mechanical thermostat for charging a thermal energy storage system. My outline, my presentation outline is as shown there. It's known that energy for cooking is a challenge in most developing countries because they normally use wood fuel as the source of energy for cooking, and the use of wood fuel always requires cutting trees, and this has led to a devastating rate of deforestation. Among other energy sources that could be used, there is hydropower, geothermal, wood fuel, solar energy, petroleum products. But among all these, solar energy is the only source that is available everywhere on the Earth's surface. It has been shown that most developing countries have a high solar energy potential, and this solar energy can be stored as either electrical energy in form of in the batteries, or as thermal energy in thermal energy storage systems. Those are the test systems. But cooking using an electric battery is expensive, so therefore the test systems are preferred. These test systems are categorized as sensible heat material, phase change materials, and thermochemical processes. But of these three, the first two, sensible heat and phase change materials, are the ones that have been developed so far currently. Of these that are developed, they are not yet widely accepted due to some challenges. And so far, in those that are developed, it's usually not one material being used for heat storage and for heat transfer. So oil-based systems could be preferred in this case because it is the same material that could be used for heat transfer as well as for heat storage. Now, so long as it meets the standards, the required prerequisite for the oil to be used in a test system. Now, this is one of the shortcomings that the existing test systems are having is ensuring that they have a higher thermal stratification. It has been found that the performance of sensible test systems increases with thermal stratification. The efficiency of these test systems, the thermal extraction efficiency increases with thermal stratification. There are different methods that are available to measure thermal stratification. Of all these methods, it can be shown that if a test system is charged at a constant temperature, thermal stratification is guaranteed. There have been attempts to charge a test system at a constant temperature, and a charging temperature range of 50% has been achieved. There are questions that why don't we use the commercially available solenoid valves, but these valves, they are designed to work at temperatures not exceeding 100, because mostly they are used in washing machines. Yet our test systems, they work at temperatures much higher, that is 200 to 350 degrees. So that means there is need to develop a mechanical thermostat for charging an oil-based test system at a constant temperature. Now there I have the schematic diagram of the mechanical thermostat that we developed to charge a test system at an average constant temperature. It is composed of mainly four components, and that is the heating chamber, which we can see as the blue, the red line, the red section, the expansion system, which is composed of, in general, I'll call it a sensor and an actuator, and then the slider valve is what is activated to open and let the hot oil into the test system. Then the adjusting knob, which is meant to set the charging temperature to a value of interest. So these four components, first of all, the heating chamber was constructed by having a cylindrical, rectangular-based cylindrical cylinder with a heater fixed at the bottom, and it is open at the top to the atmosphere, and then with an cold oil inlet at the bottom and the hot oil outlet at the top. Of course, we shall use some couples to measure the temperature. The second component of this mechanical thermostat, the expansion system, which is to act as our sensor at the same time as our actuator. It is composed of a copper coil, which at one end it has a closing tab, and at the other end it's connected to a pneumatic cylinder. This pneumatic cylinder, it has a plunger in that the oil which is tapped in this copper coil, when it gets heated, it expands, and then this plunger creates a movement, a to and fro movement during the heating and cooling. So that is our sensor, at the same time our actuator. Then the slider valve, this is which is supposed to open to let hot oil into the test system or let it not go into the test system. Here we have its schematic diagram, which shows when it is closed, and then when it is open by a sliding mechanism, and then we have its photo when it is assembled. The adjusting knob, which is used to set the charging temperature, in this case, it is set by increasing or decreasing the distance between the pneumatic cylinder, that is A, and the slider valve. So these knobs that are labeled B are the ones that we adjust to increase or decrease that distance. So the fully assembled experimental setup is as shown there, and in this case, if I follow the schematic diagram to the experimental setup, we have the coiled oil which comes in through valve 1. When valve 1 is open, it is somewhere there, and then in the heating chamber, this oil will get heated, where hot oil always rises to the top. When it is at the top, it is in contact with the copper coil, so the oil in the copper oil will get also heated. When it is heated, it expands, and the plunger of the pneumatic cylinder, that is the piston load, will extend due to the expansion. When it expands, it opens the slider valve, and then when the slider valve opens at a given temperature, then this hot oil can flow to the test system. The temperatures at the top of the heating chamber, at the bottom of the heating chamber, and at the outlet of the slider valve could be recorded. Now, in the operation of this cylinder, I would say the oil flows from the coil oil to the test system according to the Darcy-Weisbach equation, which is given there. The oil in the expansion system, that's in the copper coil, it expands according to its equation, of which V is the volume, alpha is the coefficient of volume expansion, and delta T is the change in temperature. The energy, in the beginning, there is no flow. In the beginning, there is no flow because the slider valve is closed. And when it is open, there is a flow. So you have two possible scenarios, the transient state and the steady state. In this case, in the transient state, that's when there is no flow. The energy balance is governed by this equation. And then in the steady state, we have a flow. And the energy balance is governed by this equation. The first term, we have rho, which is density, C specific heat capacity, A, the cross-sectional area of the heating chamber, HT is the height of the heating chamber, and this T is average temperature at a given time, and Ti is the initial temperature. And then this other term is for the heat loss, where U is the heat transfer coefficient, A is the surface area of that. The only different term in the second in the second equation is the flow rate. That's V, mass flow rate, of which T1 is the temperature at the top of the heating chamber, T3 is the temperature at the bottom of the heating chamber. So those temperatures were measured initially, and we found that we could have, we obtained an oscillatory mode of charging the test system. And we can see here that the temperature at the top of the heating chamber increased. It was increasing before the slider valve opened. When it opened, cold oil came in, and then it began to cool. On cooling, the oil in the copper oil constructs, and then the slider valve closes, and then we have heating again. So that's why we have this oscillating mode of charging the test system. And a similar mode is observed for the three temperatures, except at the bottom here, we only have an increase in temperature when the slider valve is closed, because when it is closed, the oil at the top begins to conduct to the bottom. We can
4 minutes.
You can even see we can even see at the volume of oil that is collected in the test system. In that here it was when the slider valve opens, we have an increase in the volume, then it closes, an increase in volume instantly. So this was our first graph, but remember we need to charge it at around 200 degrees centigrade. So we increased and we obtained a value, a graph that looks like this, close to 100. But remember, our point is to charge at a constant temperature. So what we did, we used a valve which was partially opened to set the maximum flow rate to a lower value. And when we did that, that's when we were able to obtain a charging temperature which is nearly constant at 100, at 200. In this case, initially we had a fluctuation range of 50, but after 30 minutes, the temperature range, the charging temperature range was at around 14 degrees centigrade. So in all, we can say that we were able to develop a mechanical thermostat that could charge an oil-based test system at a temperature range of 14 degrees centigrade, which is a bit an improvement to the previous value of 50 from the previous experiments. And if you use it, if you are to use it to assess if it can cook any food, you have to know how many minutes it takes to open. In this case, it was 80 minutes. In the oscillation mode, the oscillating period would increase. Although it was around 80 minutes, the increase was small. It also required about 0.1 kilowatt hour to open the slider valve, and
what has happened? Tuseme? Oh, looks like you have lost. Yeah.
Thank you. I'd like to acknowledge to thank the sponsor, that's the International Science Program through the UG01 project, that's under Msseesa, and the Norwegian Agency for Development Cooperation, that's NORAD, through the Energy and Petroleum MP project, Capacity 5. Thank you.
Okay, thank you. I'm reminded that David is back. So can David please present? David? Is David in now? No response. Is David around now?
He's there. He's there.
Okay.
We see him.
Okay,
David
fine. So share your screen, please.
He needs to unmute and talk himself. Osio, unmute. David? Unmute, David.
What has happened to David?
He's not responding.
Maybe he's muted.
Let's see what we can do. Let's approve.
I'm unmute.
Let's see how that he's going to talk.
I can't get you, David.
I'm getting you. No, we are projecting this from our end.
So, oh, I see.
Yeah.
So can you contact them? Can you contact one of those guys there?
Let's just contact the supervisor to see.
Okay, yes.
Yes, I'm on the screen. David, Osio.
We are not hearing.
End of the call because he may be using the internet.
Ah. Yes, David, please, can you go ahead and present? Oh, unmute, please. Unmute yourself. Can someone help? Good.
David, remove the earphones and use the computer audio. Remove the earphones.
Yes, please. Can you go ahead? I can see you. Oh. Professor Wambora, what is the problem?
Just send a chat and tell us what's happening.
Yeah. Professor Wambora?
Yes.
Can you just find out, please, what is happening? Because I can see this gentleman, but I can't hear what he's saying.
Yeah, we also see him, but we can't hear. So,
Is he saying anything?
I don't know what's going on.
Is he able to hear us?
He can quit and join. David, maybe you can quit and join again. It'll take time. Huh? Okay. Oh, join with the phone. David, since we are projecting for you, join with the phone. I think, Dr. Tambo, maybe
Yes,
we
please.
can call questions, discussions.
Okay, I think so. I think so. Okay. Ladies and gentlemen, looks like we have lost David, although I can see him, but he can't be heard. Now, let's go back to the questions and clarification session for the three presenters who presented this afternoon. Can we, I will now open the floor for questions and discussions. Yes, please. Tell us your name, where you come from. The floor is open, please. The floor is open. Maybe I can start with the Pamela. Is she around? Pamela?
Yes, I'm around.
Yes. Can you go to slide number 12?
Yes, I'm here.
Yes. Go to your slide number 12, please.
I've answered yes.
Okay, that's correct. Now, if I look at your types of fuel wood, I mean the wood, the fuel there, we are on technology. We have the 3-stone fire, we have kiln stove, we have all metal stove, we have fire day stove, and the combination of clay and metal. And I think there's the last one also there. If you go to rural areas, typical rural areas, you still see that the technology number one is so predominant there, so common. What is the reason for that? Although, according to your results here, I agree with you, LPG is the best for cooking, but why do we see the technology number one to be so much outstanding in rural areas?
Did I get you right? You're asking why firewood?
Yeah, the technology number one.
Wi-Fi is common in rural areas.
Yeah, why is
that
it so
question,
common?
Doctor? Is it the issue of three-stone fire or the fuel, or the combination of the technology and the fuel? I didn't get you well.
I'm just seeing the figures there. If you would see the final figures there, we are saying that for the best technology there is the LPG or the burner
that's
stove,
right.
okay? But still more, why do we see technology number one there, the three stove fire, to be so common in rural areas?
Yes, it is common because it is what they have. It is cheap. They actually build them themselves. Just need a stable three stones, and then the firewood is also easily accessible. I hope I've got you right.
Okay.
So the three-stone fire is commonly used, the traditional three-stone fire. The kiln stove is an improved version where you build out of clay and the efficiency increases as compared to the three-stone fire.
Okay, so talking about
Did I answer
availability,
you?
so available. Okay, so that's fine. I'm satisfied.
Okay, thank you.
Yes, please. Any more comments, questions?
Yes, everyone. My name is Nathaniel Congo from the University of Dar es Salaam. First, I congratulate Pamela for the good work, but I have a small question. I would like to know the effect of food storage time against the fuel consumption on cooking.
You asked the effect of fuel storage
time.
Fuel storage time
for 1 year or 2 weeks, 1 week, maybe all dry, but the storage time is different.
Fuel
What is
storage
the
time
effect
on cooking
storage
time?
for fuel consumption?
Can you please kindly put that on chat if it is okay?
Yeah, please. Yeah, I'm going to write the question on the chat here, maybe. Any more questions, please? Clarifications? The floor is open on all the three presenters. I take it that we are all satisfied. So, am I seeing David? It looks like I'm seeing David somewhere. David, are you now ready to present? No. Okay. So, I think this marks the end of this session. I hand over the mic to Professor Babora, please. Can you continue with the updates?
Yeah. Thank you very much, Chair, for this session. David, I see he's struggling to speak.
Yeah,
but
I can see him also, yes.
Yeah, he's struggling, but we can't hear him. So I think he has issues. Maybe if he sorts out his issues, we can allow him to present tomorrow. Yeah, so I think this is the end of the session. I want to thank all the speakers and the chairs of session and rapporteurs for the good management of the sessions. So tomorrow is our last day of the conference. We begin at 8:30, but let's log in before then. We have one keynote from Oh yeah, okay. So we have one keynote from Professor Prem Jain, University of Zambia. And then we have some papers from students, around 4 or 5. So we'll finish early, around 11, and then we close. We have a closing session. But before that, maybe before we close for today, I want us to take a picture for remembrance, for our records. So can all of us please have your videos on so that we take pictures? Let's have our videos on. Let's have our videos on for the camera. Let's have our videos on, please. Sai Ngesa. Pamela, we are not seeing your face. Sylvester Tombo, the chair of the session, we are not seeing.
We are taking together with Pamela.
Pamela, Sylvester.
Pamela and Robinson are together.
Oh, Pamela, you are together. Robinson and Ammonia.
Yes, with Robinson.
Okay, fine, I see that. I see that. Sylvester, can't see you. We want to see your picture. Okay, as they are taking the pictures, tomorrow's chair session is Dr. Onesmus Munyati of the University of Zambia, and the rapporteur is Dr. Elijah Ayeta from the University of Nairobi. And then we will have a keynote from Professor Prem, University of Zambia. I think we have taken pictures now. Have we taken pictures? We have taken pictures now. Thank you very much, and have a good evening. Bye.